Hello, I'm Sue Nelson, and this is a rather special edition of the Create the Future podcast, because my guests are the winners of the 2019 Queen Elizabeth Prize for Engineering, awarded for the development of the Global Positioning System, GPS. It's the first global satellite radio navigation system, a huge engineering infrastructure. And if you've got a smartphone, it gives you both your exact location and the precise time within billionths of a second. It's used for everything from navigation and banking to precision farming and science. As you might imagine, there are several crucial components to GPS. It uses a constellation of orbiting satellites, ground stations, a receiving device, and an atomic clock. And I'm delighted to be joined by three of the engineering pioneers who spearheaded the advances that culminated in an invention that revolutionised the world and benefited humanity. They are Bradford Parkinson, Dick Schwartz, and Hugo Fruhauf. First of all, congratulations to you all. The Queen Elizabeth Prize is a considerable accolade. Is it special winning a prize like this?
Well, I would say it is without a doubt a prize that is unexcelled by anything else, particularly for engineers. We don't win Nobels because generally we make stuff that work. That's supposed to be a joke, but it probably doesn't work.
No.
But nonetheless, I personally am, this Brad Parkinson, I am deeply, deeply honored. And the ceremony was impressive, and the whole reception of what we have done was obviously well rehearsed, and it gave me a great feeling about what a team of engineers had produced.
Did you ever think that you, Dick, that you would be at Buckingham Palace?
Did I? No, I never thought I'd be at Buckingham Palace. I grew up in New York City, and Buckingham Palace was the other side of the world. No, I never thought I'd had. It was quite impressive, the ceremony. The Prince of Wales is a very, very impressive person and very congenial, very, very easy to talk to. And so the honor is outstanding, just outstanding.
That's wonderful. Well, Bradford, let's start with you, because I'm going to start chronologically. You're a colonel in the United States Air Force, a graduate in engineering from the U.S. Naval Academy, and your role came from working for something called navstar. Can you explain what navstar was?
Well, that's a name that we gave to a satellite-based navigation system. It turns out that the name itself was generated because one of the persons that I had to get to yes to give us the money to produce it suggested the name. So I said, okay, if you like navstar, that's what we're going to call it. And, of course, the idea was if he had called it that, perhaps he would approve. And he ended up approving.
So is it short for navigation using the stars, which is what you might guess from that?
No, it was just a nice name. And on the other hand, GPS had a real meaning, global positioning system. It was global, and it was positioning. And it was a system in the sense that a user would supplement it with a receiver, and as a result of listening to at least 4 satellites, you could figure out where you were anywhere in the whole world.
So how did navstar become GPS? Was it a straightforward switch of name, or did you have to sort of go through specific
The names
roles?
were used in parallel, and it was evidently my prerogative. I was running the program, and I decided what it was going to be named, and I have a law of the assumed decision, which is if there's a vacuum in decision-making, you simply make the decision and move on. And unless someone stops you, you keep running.
Obviously, in terms of designing and developing the system, what for you was the most challenging part? Because that's, an enormous project to bring together.
Actually, a project like this has a balance of very difficult things, and it depends on whether you're talking about the satellite. The satellite was probably the clocks, although Dick Schwartz was responsible for making the whole satellite reliable, and that was essential if it was to be affordable. On the other hand, the ground control system had to calibrate where the satellite was going to be 90,000 miles into the future, and the user equipment had to listen to those receivers, those ranges, listen to the signals coming from satellites, and from that derive information that positioned it to perhaps a few meters. And along the way, by the way, it has to correct for both the general and special theories of relativity. And were it not to do that, you would be miles off.
As an engineer, what skill set did you find was the most useful? I know mathematics is a key part here, but you've got physics with relativity, you've got your engineering as well, the application.
I was trained as a space engineer and as a controls engineer, and both of those I found to be very useful. In the case of controls, the estimation of position, the calculation of position. In our books, I wrote the error analysis for GPS. So all that was useful. But as well, knowledge of how you get into space, what Kepler's laws are all about, how a rocket works, that's pretty fundamental. But we had to listen and think about that a great deal because Dick's satellite had to fit on the top of a booster and it had to make it all the way up or we weren't going to have a system.
So in terms of Dick, it's a good point to pass over now because you joined an aerospace company, Rockwell.
That's correct.
In 1957. So what were you doing then when this was going on? What were you doing at Rockwell?
The company first, it started as North American Aviation and later became Rockwell from a name thing. When I joined, I worked on the Apollo program, and Rockwell, North American Rockwell at that time, managed a capsule, but they also managed a second stage booster. And I worked on the second stage booster, and as that program kind of wound down at the end of the 60s, the beginning of the 70s, we started to pursue other things, and we pursued satellites, and GPS came along right at that opportune time, and we were fortunate enough to win the GPS satellite program, and then went forward with that.
What was the obstacle at the time for putting satellites into orbiting the Earth and to distribute GPS signals?
The obstacle, I guess, was don't let them fail. That was the main thing. No, they'll get them up so they're working. And
it's also the environment, isn't it?
Well, there's an environment, but there were some constraints. He mentioned the boosters. The Air Force was working on a limited budget, so they got some old boosters out of their silos, that, initially ballistic missiles. That limited the amount of weight you could put up. So that said how much weight you could put up. And then we had to go through all the shaking and rattling and all the stuff to get up and have them not break. We had to recognize we were working in the Van Allen belt, and so we had to protect the components. And I think the most difficult thing is, or maybe the most fun thing, is setting a very, very high standard for the people that perfection was the name of the game. We couldn't fail, and that actually turned out to be a lot of fun, where people almost worked together and challenged each other to, is it right? And we worked at that, and it turned out it was. It was relatively short term to put together. The pleasure, me personally working on it, some of these aerospace programs, airplane programs are 20-plus year programs. From start, piece of paper, to putting the first satellite up was 44 months. So our group of people could see the beginning and the end. There are people in the industry who see the beginning, not the end, or see the end and not the beginning. But it went from paper to flying to producing the signal. It's a very, very rewarding experience. And the experience was not eureka. It was kind of one's up, two's up, three's up, four's up. Then it was eureka that they all worked and you could navigate.
Doesn't that describe engineering, though, Bradford?
Well, that does describe engineering, and I should make a comment on selecting Dick Schwartz and Rockwell, because there were four companies that wanted to build our satellites, and of those four, his was the second highest price. And he won because I persuaded the authorities that he was the company, or he represented the company, that was most apt to succeed. And I have never had any remorse whatsoever about having made that decision. He indeed was a wonderful program manager to work with. He had a reputation that if something, his statement was, if something is broke, we're going to fix it, but we're not going to hide anything from anyone. And there were some contractors that had a reputation that they didn't want the Air Force to know they had done something bad. He never did that. In essence, from beginning to end, it was an open teamwork environment, and I think that's what led to success. Having 4 first-of-a-kind satellites all operate virtually flawlessly is almost unheard of. Initial failures, infant mortality frequently happens, and not only that, by placing the satellite in the upper end Van Allen belt, we were putting it into the harshest environment you can imagine. For example, if you were a human unprotected at that altitude, not including the vacuum of space, radiation would kill you in less than a minute. This is very, very hot region. And to make the electronics work required a lot of care and feeding, and his people did it.
I wanted to say something just on that, the management of it. Our technique at the beginning was on Monday mornings at 8:30 we'd have an internal meeting of all the people responsible for all the elements of the satellite, and they'd produce, what did I do last week, what am I going to do next week, and what's my problems. And we go through that, and then the Air Force would visit me in the afternoon, and I kind of repeat everything so they'd be up to speed on it. And I get to the end of Monday, and I hadn't done a lick of work, And I said, well, why don't, to get it firsthand, they don't have to take my interpretation, the Air Force, why don't you just join my meeting? But there's only one requirement. You cannot speak. You can listen, and then you can come to my office after the meeting and say anything you want to me, but you can't take over the meeting or we'll get back to where we were. And that turned out because they heard everything firsthand, raw data, raw information, and they were pleased, and they got used to not speaking even.
Not really.
Going back to the hardening of the spacecraft, how did you actually do it? What did it involve?
Well, putting metal around these critical components and shielding them.
You make that sound very simple.
It turns out to be weight, that kind of stuff, and weight is very critical, so you can't just pack them all in lead. And then we tested them on the ground, and it worked.
And you improved the antenna as well.
Well, the antenna, if you're flying up there, right below you is pretty close. The edge of the Earth is pretty far away. So we had a pretty good antenna designer. He kind of designed the antenna with a bit of a hole in it, so it produced a little power down here, but spread the rest of the power out to the edge. So there's essentially equal power from edge of Earth to edge of Earth, which is a long way off. That, I think, was one of the kind of inventions of GPS.
Hugo, you're an electronic engineer,
right?
And you joined Rockwell International in 1965, and you were working on the Saturn V rocket. What were you doing?
Well, first of all, Dick was my boss at the time, and Rockwell had won the contract for the second stage. Rockwell was into everything. They had the Apollo capsule itself, and they also had the second stage of the huge rocket. It was a liquid hydrogen, liquid oxygen, high-energy stage, so we kind of absorbed all the sins of the other people, with extra weight. We were able to, had enough lift to be able to, have some problem solved. And what I was assigned to do is to static fire the vehicles several times in order to find whatever glitch there is. The vehicles are so big that you cannot transfer them by land. So the vehicle that was made by Rockwell was done in Seal Beach, California, and it had to go through the Panama Canal, through the Gulf of Mexico, Mississippi River, Pearl River, and about 30 miles. We actually had to dig a 30-mile canal. And those huge things, which are, like 40 feet in diameter and about 100 feet tall, are then on barges, and they go through that whole process. And for our particular stage, since you're asking about us, it went the journey through all of those things, and then there's a crane waiting for it, which lifts the vehicle out into a huge test stand. And the whole idea is to make it think it's flying, even though it has, it goes off at 100,000 feet. But we did everything. We count down, do everything around, do all the necessary testing for the home office that, did a fantastic job designing it. And in 1967, 68, I was the chief test conductor, at Mississippi, working for Dick. And basically I kissed all the stages that went to the moon. And then they go back, on the barge, and then they get floated all the way around Florida there, and put it in vertical assembly building where everything is stacked up, and then you saw that little, crack tractor that puts it back out.
Yeah. I've been in the VAB, actually. Yeah.
So once you get it tested, God has to give you permission to do anything to that vehicle, move a wire or anything. Once you're done, you can't do much more in the vertical assembly building. And I think any major problem you would not fix it there. You'd probably send it back.
I must admit, I'm going to do a bit of a fangirl here. I can't believe I'm with people here who've worked on Apollo and Saturn V. This is just,
Gives you goosebumps. I get goosebumps talking to you about this.
It does. And also it's amazing because your background includes something that was involved with the moon landings and GPS. I mean, this is astonishing in terms of what you've done. So how did you, go from that to GPS? Were you just told what to do by Dick?
No, he only made sure that I had ties that were completely, accurate between here. That's a joke last night. But anyway, actually, I had 5 years of launching experience before I came to Rockwell. So we were launching Atlas Aeginas and spy satellites out of Vandenberg. How we get to GPS? Well, we were very, very busy for the last launches, and the Apollo 17 never really went. And at that point in time, we started looking at things to build in the future. We were building some small satellite programs that never went really anywhere. And then the government puts out what's called requests for information, RFIs. And so after a while, things get kind of technically leveled, So you hear a little bit from RCA and you hear a little bit from Philke Ford, and some of it is on purpose and some of it's not. But anyway, it starts to get the people that are, not government involved. And then finally, after that process for about a year, then they put out a request for a proposal. And Dick had the guts for us to actually think we could win this. We had never built a satellite, 3-axis stabilized satellite like that before. And selected a team, and thank God he chose me to be a chief engineer again, and so away we went. What
was Dick like as a boss? I know he's sitting next to you, but...
What about him? I basically hate his guts, but he is so daggone good. You just got to forgive him for all that, and just, you learn so much. He basically formed my career. I mean, I've had a fabulous 60-year career, and I'm still not retired.
Dick, your ear's burning.
Go back to the second stage of the Apollo vehicle. There's something called the mass fraction when you build a booster. What you'd really like to have is a balloon full of propellant so that the booster weighs nothing. So the second stage had the thinnest walls, the most propellant, and had the highest mass fraction of anything in it. So it was very tender to handle, and that was part of the challenge. On the satellite stuff, we went after it, and I think putting together a team was the thing that did it. People who were interested in doing the work and who had a perfectionism in them, and they wouldn't let go unless it was correct. And, Brad Parkinson talked about we did not ever have problems under the table. Any problems we had was up on the table. I always said if you stick them under the rug, they get pretty smelly in a hurry. So you might as well put them up on the table and deal with them.
I must admit, I liked the way engineering is always about teamwork, but I also like the way that Brad said that it was just unusual with contractors that they didn't go for the lowest bidder, that they went for the second highest bidder. Particularly within the space industry, that famous joke by John Glenn, I think it was, saying he was sitting on top of a rocket that had been built by the lowest bidder or what have you.
Yeah, but he sounded very generous when he said that. We won the first contract for 4 satellites for $42 million. Just think about that.
It costs, the latest GPS-3 right now costs almost $1 billion.
Oh, my goodness. So what you're saying is that they got it cheap at half the price then, basically. Yeah. Hugo, the key for accurate timing at the heart of a GPS satellite, they needed an extremely accurate method of timekeeping, an atomic clock. But there was a shortcoming, wasn't there, at the time for using an atomic clock on a spacecraft?
There was a very smart German in Munich that came over to the United States, and he made this he made a laboratory piece of equipment that was like twice the size of a microwave into a very small 4x4x4 inch. And through relationships, I'm a German and I could speak the language. And he was, and he wasn't all that good in English and stuff. I was tipped off by one of my employees. He was a fellow that worked on my staff, and he kept saying, I was going all around the country, including HP, trying to let them have help from them to build something smaller than the laboratory piece of equipment they had. And I got absolutely nowhere. And I was actually worried. I was afraid that this, without that, we weren't going to be able to fly, because Brad had a lot of problems with money, and so therefore he assigned 21 Atlas F ICBMs that they had in stock they weren't going to use. And we had to fly on an ICBM that only had 1,450 pounds of throw weight. So the satellite, by the time you have another kick motor that puts it into this 20,140 mile orbit, the satellite could only weigh 850 pounds. So my problem was even bigger, because today they weigh 4,000 pounds, and so you could put anything you want on it today, but then,
so it was all about miniaturization.
A 50-pound clock, 3 clocks, took maybe 20% of my weight. And he kept saying, go see this guy, Ernst Yeacher. He's got this little thing, and of course what he said just didn't make any sense, because it was just too much. It's like something falling out of heaven, So I finally went, and what I saw that day was I was just blown away. I mean, I got emotional. I got just so much luck. It could not happen to one time. So I got home that night, and I get this phone call, and Ernst is swearing at me with every 40-syllable German swear word, and he was just upset. Next day I go in and I said, Ernst, what's going on? Wie geht's? Was los? And he said, You're trying to trick me. And I said, what do you mean? Apparently this guy that was working for me was working for another company to which Ernst was selling these small things for about $3,500, and they were trying to reverse engineer it. And he saw that guy in the laboratory when he went over to his customer, and he thought we were pulling a joke. Of course, he had the responsibility to tell me that he was moonlighting at night. So I felt no remorse about, walking him out the door 4 hours later. Long story short, then, having his knowledge, I sucked him dry for everything he knew, and basically began to realize that this is our answer. And at that point in time, we had him do a physics that I personally made better, and then we made a deal with them and one of our Rockwell divisions, Aeronautics, and together then, taking some of his parts, we designed a whole new package around it that was radiation hardened, both for neutron fluence, total dose, and flash.
And what was the answer? What was it?
What the answer is, we got down to a size that was about 5 by 5 by 6, slightly bigger than what he had. Basically, today we pay $4 million per clocks. At that time, can you imagine what Dixer said? It was.
How did you do it though? How did you get from something that was huge to doing the same thing but lighter? I mean, what was it?
Smart engineering on the Germans' part that we then excelled and went nuts with.
So was it much lighter materials all round? Did you have to change?
No, he changed. He changed the game. He went from large tubes, rubidium vapor oscillator uses a lamp and a glass cell that's about the size of my thumb. Well, the other guys had cells 6 inches by 4 inches, and they never tried the fact that you could maybe make that 100 times smaller. And then some of the stuff that I had learned added together, and now you could suddenly make that same thing instead of the lamp that lights the whole thing up in the physics, to be the size of a light bulb. All of a sudden, it's the size of your fingernail, that kind of thing. So there was a good team relationship there, which was thinking out of the box. As a matter of fact, the German product, and they could have It was done by Rohde & Schwarz, famous company, and Ernst began to realize that they weren't really interested in this thing. So he gave them the reward money back and said, "Can I have the patent? I'd like to do something with that." Rohde & Schwarz had absolutely no use for something that was 4 by 4 by inches that worked as good as a lab device.
And this is where actually your experience of working in space really helped.
He keeps referring to it as a German. His name was Ernst Jäger, and he was a genuine genius, absolutely genius. He was fantastic. He knew his stuff in spades. And if you could get that and extract it, and that's what Hugo did and put it together. But he was one of the heroes of GPS.
He died in 1993, and I think it was a loss of a national asset. I would put it in that framework. And the reason for that is that Dick and I worked together. And he was a German. He had a German company, and Americans don't go for military equipment to foreign country. So we actually contacted Governor Brown's son in the 70s, and we ended up we had so much hassle. There was a guy that told me one time I went to the Pentagon that it's not going to happen. We're not going to fly German hardware. Of course at that time it was American made, but. So we got to work on it, and we ended up getting him citizenship papers in 2 weeks. So he was a citizen 6 months after he came to the United States. So there was somebody else that was thinking he was a national asset.
Absolutely, absolutely. There was another important aspect involved in enabling GPS to operate successfully, and that was designing a signal for civilian use. It involved building the receiver that processed the first GPS signal using something called code division multiple access, which is essential for accuracy. And James Spilker was involved in that process, and a key component, in fact. Sadly, James passed away a few months ago, but I'm delighted that his wife, Anna Marie, is with us to pay tribute to James. He knew, didn't he, that obviously that he'd got the award because it was announced early in February. How did he receive that news?
He was thrilled, delighted, and more importantly, he acknowledged the importance of this award to recognize engineering globally. And he personally wanted to thank Queen Elizabeth many, many times for putting her name on this prestigious award.
It is important, that, isn't it? It like you said, Bradford, at the beginning, that there isn't a Nobel Prize for engineering, which is sort of outrageous, which is where this has filled the gap.
So engineers are an interesting lot. By and large, I believe they're driven by achievement, by making something work. And that excites them more than the fact that everyone knows they did it. If they know they did it, there's a deep inner satisfaction. So engineers as a group tend to be anonymous. But at the same time, they don't necessarily invent things. What they do is take little pieces of invention and combine them in creative new ways, make them robust, reliable, and useful. And as a result, the engineer turns around and gets his derived satisfaction from seeing that something is working and benefiting humanity. And in the case of GPS, I think all of us who worked on it recognized it probably would help humanity. And, of course, what's happened in the intervening 45 years or so, it's shown that in spades. It's even gotten to the point that GPS is taken for granted. Your knowledge of where you are, you whip out your cell phone, and there you are. We asked a cab driver today. He was using GPS to get from one place to another in London, and I said, well, do you know how that works? And there was a long pause. And he said, no, not exactly. I think it has something to do with satellites. So that's fine, because he doesn't have to know. Instead, seamlessly, he takes it for granted.
And in terms of James Spilker's contribution, how important was this code division multiple access?
The important part was not code division multiple access per se. It was that he understood the family of codes well enough to recognize what we had to do to make it robust. And he did that extremely well, and not only did he do that, He also, and this hasn't been emphasized, was the person who built our first reference stations, which were used to monitor the satellites and from that derive the prediction of where they were going to go. So he made a number of important contributions, but those two really stand out in my mind.
Now, he was an electrical engineer, co-founded Stanford Telecommunications, professor at Stanford, co-founded the Stanford University Center for Position Navigation Time. It sounds like everybody around this table, that he had an incredible career as a man. Anna, what was he like?
Well, the emphasis for Jim was to get the work done, to do the work of engineering, and to do it to the best of his abilities. And that was his satisfaction. And of course, he was grateful for people to acknowledge his contribution, but was not his motivation. His motivation was to design the system so that it would work, to teach others his knowledge, and to mentor. So that's what he did with his company of about 1,400 people. Half of the employees, approximately, were PhD graduates. The other half were the support team. He mentored everyone, and he was and many of his employees related that working at Stanford Telecommunications was the best job they ever had. And then others said that it was like getting another PhD. Jim challenged them continually. And more importantly, he had an open door policy so that any of the employees, if they felt like they were stuck and they couldn't figure it out, they could come to him directly.
It sounds an incredible man. Did he take that engineering home with him? Could you get him to relax?
His form of relaxation was to work on his physical strength. So he went to the gym practically every other day, worked out an hour and a half, and acquired the skills of bodybuilding, and he became a national champion. He acquired titles, national titles in bodybuilding at the age of 65.
Wow, I did not know that. He sounds incredible. Yeah, well, thank you so much for sharing that lovely nugget. I have this beautiful picture in my head now of this bodybuilding engineer.
You're welcome.
Now, I know you've had several receptions in London while you've been here, and obviously receiving the Queen Elizabeth Prize for Engineering. And some of the people who are present and some of the people from the Royal Academy of Engineering have got quite a few questions for you. So I'm just going to play some of those questions and see if you can answer. Well, see if you can. I know you'll be able to answer them.
Hi, my name's Robin. I'm the Public Affairs Advisor at the Royal Academy of Engineering, and my question is, would GPS ever work in the interior of the Earth? And if not, why not?
Jane Sutton from the Royal Academy of Engineering. Will GPS work in outer space?
Bradford.
The RF signals that GPS uses, it turns out, are at L-band and penetrate the ground very, very little. So in terms of working in that sense, the answer is no. But the second question regarding use in space was actually a bit of a surprise. And it turns out that you can put GPS receivers into satellites. One of my PhD students at Stanford demonstrated this. And the idea is that a GPS receiver in orbit around the Earth is also bathed by the same signals as GPS, provided it's underneath that constellation at a lower altitude. What we didn't realize is that even at higher altitudes you can pick up on the GPS signal, and NASA today is working on receivers that will operate almost all the way to the moon and still receive the GPS signal and navigate. And it turns out that's extremely valuable because it makes a otherwise hard job very simple.
I'm Stephanie Hauser. I'm a graduate student at the University of Iowa, and I was wondering how you think that GPS can be best used in the developing world to solve some of the issues that we face in peri-urban settlements.
Dick.
GPS is worldwide. So right away they start off with something that they didn't have to build from scratch. It's like plugging a light bulb into the wall. It's a brand new thing for everybody. So they got that to start with, all that intelligence, and they can do anything they want to do with positioning, from farming to autonomous cars to whatever. Their ingenuity can take over at that point. But they don't have to build an electric farm or something like that. They got that. Effectively,
you've provided the tool, and it's up to them what they do with that tool.
Yeah, and GPS has interesting possibilities. The two areas that I would focus in on is space navigation. I'm not saying that you navigate on the moon, but as Brad was saying, the spillover, the signal of GPS illuminates a globe, but more than that. It has a 15-degree more. So now that signal spills out. So now you got a satellite on the other side of the globe over here, and I'm actually getting the spill out because it's going past the navigation of the globe and then spilling out into space. And as Brad was saying, there's work so we can more accurately target the moon and target, especially the moon right now, signal strength is an issue. And so that way, a new application. Another application, in my opinion, is autonomous platforms. Now, the application there is slightly different, and that is that in an autonomous platform, GPS is the only sensor that the platform doesn't control. They receive it. So that means that there is a possibility that they can't receive it for whatever reason, jamming or whatever. So I think that whole process with GPS interacting with autonomous platforms means that GPS signal is going to be aided with all kinds of things. Like yesterday we saw these scanning systems that the UK is doing. Well, you'll have terrain recognition. You'll have accelerometers. You have inertial measurement systems. You have LiDAR, radar, and sound. So you have all these things which will integrate with GPS. So when it's gone, the platform can continue as it was, and then GPS for some comes back because we found whoever was jamming, and now it retunes it. And so to me, GPS is going to get more and more robust everywhere. Because they're not just going to be using a GPS receiver. You'll have a chip that has all these other things in it that aid navigation.
Hi, my name is Titi, and I'm a QA Prize ambassador. So my question is, what is the weirdest application of GPS that you've ever thought of?
Yeah, the measuring of the Earth's plates to millimeters of accuracy. That's almost unfathomable. And they're using it today.
Tectonic plate movement, and of course faults and measuring faults. We have a fault about 100 miles from our house, and it's San Andreas Fault, and it's moving about a centimeter a year. That's a big number. By the way, China, I believe we're moving closer to China almost 6 inches every year, which is, and that's all being done by GPS.
As somebody who's involved in the miniaturization of the atomic clock, was it ever conceivable at one point that GPS everyone would have something in their pocket that would use it?
No, the GPS thing, if you got a history of the receivers, be very interesting to just look at them in pictures. The first one was $100,000 or more, gigantic. Then when we started working on it, the Army was going to use it, and I still have pictures someplace of a soldier with a 40-pound backpack and a gigantic antenna sticking out like out of your car, and he was going to be lugging that around. And then it got better than that. We used to go to these GPS conferences, and they were building military receivers for these folks, and they were pretty heavy. And their parents were sending these kids, soldiers, over Garmin receivers that they could hold in one hand. And the soldiers, you go to those meetings, and you got the scientists who design, but they have a section with the warfighters, the guys who actually been using them. And those guys, they don't mince things. I use the Garmin. If I go on my vehicle, my car, my whatever I'm on, I can use the military one. But I walk on the thing, I use the Garmin. And the commercial people were trying to make it smaller and smaller, and they did a good job at it.
Hello, my name is Matt Wall. I am head of editorial and content for Vodafone UK. I'd be interested to find out what you think about the new alternatives to GPS that are coming on, like Galileo, GLONASS, the Chinese owned version of it. Are they better? Are they worse? Is GPS going to be a thing of the past? I'd like to know your views. Thanks.
Hello, Rhys Phillips here. My question is, does GPS have an expiry date? What's the lifetime of the technology? And if it does have an expiry date, what will come next?
Hugo.
Well, satellite, the first one we built had 4.7 years MMD, mean mission duration, which means roughly a 5-year life. The satellites right now, I'm doing some consulting with the government, are now made for 50. The clocks are made for 15 years, and they'll last 25. And the satellites are also 12 and a half years, but they're all expected to be well past 15.
So the expiry date basically is extending and extending.
15 years minimum for a satellite, and even our early satellites lasted 15 years.
And what do you think of the alternatives that are around, like the Chinese and Europe's trying to set up Galileo as an alternative to GPS?
It's really more the merrier.
Yeah.
The more satellites up there, you build a receiver that can receive their signals all, and instead of 30-some satellites that we got up, suddenly you got 50 up or something. That gives you better navigation, as long as you're not picky who you're using, that kind of stuff.
The receiver does all that. In other words, we have a band at 1542.75 megahertz, and everybody can play in that thing. It's like everybody's signal. The reason other people have GPSs, why would the Brits? Why would the European Union do it? It's because the GPS is more than the commercial signal. Everybody has a code, different codes. Most of the time, it's 1,023 bits, if you want to know the truth. And it's like raindrops that fall into that thing. And every satellite has different raindrops fall in different places. So everybody can navigate, like Dick said, from this clear signal. And the receiver picks the ones that are closest in time and the best position. So the receiver does all the work, and all you really need, it ends up with a solution with only 4 satellites, although it has a choice of, like Dick says, maybe 20.
Well, Bradford's had to head off for a quick media interview, so I'm going to get you in terms of the future. Dick, where do you see the future of GPS going?
I'm probably a bad one to ask because I didn't predict this future when I was working on it. But the bright people in UK and Germany and all over the world are thinking up different applications. We saw some last night that I had never seen before. So you got this new utility that has certain capability, and the ingenuity of the people is going to be unbelievable at what you can do with it. Some things you can't even imagine. I remember being visited by Cadillac Corporation, and at that time they said, can you build a receiver for $1,000? Because anybody would buy a Cadillac, they put another $1,000 on, so they'd be the only kid on the block with a navigation receiver. Would you pay $1,000 for a GPS receiver now? No way, no way. And so the miniaturization of the electronics that went on for lots of reasons and wound up in GPS for a receiver that's a couple of bucks now, compared to, I think it was 40 pounds and $40,000 when it was being built for the Army.
150.
Well, the first one was 150, but I think they got that. So it's gotten smaller and smaller with this miniaturization of electronics.
Well, I'd like to thank all our Queen Elizabeth Prize winners for joining me today. Bradford Parkinson, Dick Schwartz, Hugo Fruhauf, and of course Anna Marie Spilker on behalf of her husband, James. Next time, my guest will be the Chief Engineer of the Panama Canal Expansion Programme, Ilya de Marotta. Join me then.